Hey everyone, how are you? Today I will do this Google Brain ventilator pressure prediction competition, and I'll be doing an LSTM model with PyTorch. And about the competition, let's quickly go through it. So what do doctors do when a patient has trouble breathing? They use a ventilator to pump oxygen into a sedated patient's lungs via a tube in the windpipe. But mechanical ventilation is a clinical intensive procedure, a limitation that was prominently on display during the early days of COVID-19 pandemic. At the same time, developing new methods for controlling mechanical ventilators is prohibitively expensive even before reaching clinical trials. High-quality simulators could reduce these barriers. So this competition is all about these predicting these simulated ventilator pressure. So current simulators are trained as an ensemble where each model simulates a single lung setting. However, lungs and their attributes form a continuous space, so a parametric approach must be explored that would consider the differences in patient lungs. And about the data, alright, before that, in this competition, participants are given numerous time series of breaths and will learn to predict the airway pressure in the respiratory circuit during the breath, given the time series of control inputs. So we have been given these two files, train.csv and test.csv. Let's quickly look at train.csv. So I have individual IDs and then breath IDs, and we can see the breath IDs are duplicated because each single breath ID has multiple R value, C value, and time step. So let's go through this column name. So we have, I think, 5 features here. I have breath ID, then R, C, time step, U in, U out, and pressure. And this pressure is what we are supposed to predict. So this I'm looking at train CSV, and if I look at test CSV, all the columns are existing here as well, except the pressure column, because that's what is supposed to be predicted. And about the column names and definition, ID is a globally unique time step identifier across the entire file. Breath ID is a globally unique time step for breaths. And R, this is lung attribute indicating how restricted the airway is. Physically, this is the change in pressure per change in flow, that is air volume per time. Intuitively, one can imagine blowing up a balloon through a straw. We can change R by changing the diameter of the straw, with higher R being harder to blow. And C, that is lung attribute indicating how compliant the lung is physically. This is the change in the volume per change in pressure. Intuitively, one can imagine that the same balloon example, we can change C by changing the thickness of the balloon's latex, with higher C having thinner latex and easier to blow. Then I have U in and U out, which is U in is a control input for inspiratory solenoid valve, ranges from 0 to 100, and U out, the control input for the expiratory solenoid valve. It's a binary one, either 0 or 1. So this R attribute, this variable R, is resistance and indicates how easy it is for air to enter and then exit the balloon. Actually just move around, since during inhale exit is closed. The largest value of R is 50, has the most resistance. If we input air into a balloon with high resistance, the air stays inside and increases pressure. And if we input a spike of air, that is a lot of air are inflowed into the balloon, then the balloon with large R rise in pressure quickly, while the balloons with small r absorb the air passing through easily and do not rise in pressure quickly. And coming back to the C parameter again. So the variable C is compliance and indicates how easy it is to stretch the balloon. And that is, balloon here represent lung. The largest value of C is 50, which is easiest to stretch. If we input air into a balloon that stretches easily, the pressure does not increase because the balloon just gets bigger, and thus the air per space unit does not increase. If we input air into a balloon that does not stretch in that does not stretch, that is, for example, the C value is towards the lower end of the spectrum, for example, maybe C equal to 10, the balloon stays the same size but gets more air inside, that is, the pressure increases. So that's the interpretation of R and C. And now about the U out, this is the second control input for the expiratory solenoid valve. It is a binary variable representing whether the expiratory valve is open, that is 1, or closed, 0. So U out equal to 1 is the expiratory phase. In simple terms, expiratory phase is breathe out, or in the case of artificial lung, let the air out of that artificial lung. That's what U out is 1. So the data for expiratory phase is not helpful for the model because during the exhale, the ventilator pressure and the target pressure are nearly identical. So I have downloaded all the train and test data in my local machine. You can of course do it directly in Kaggle kernel as well. And here I'm just reading the df train, which is train.csv. So as you can see, I have 1, 2, 3, 4, 5, 6, 7 columns. Out of that, ID is ID column. So I have 6 features actually, and pressure is the target value. And this is what we are supposed to predict because the test.csv will not have these pressure columns, and this pressure column is what is being dependent on the other 5 features. And as to the structure of this project, just like my other videos, I have a main Jupyter notebook where mainly all the output I will see. Apart from that, all the util functions are defined in my utils.py, and all the training related functions are defined in train.py. So initially I have gone through the basic IDEA kind of things, that is, I have checked that there is no null values or not a number, etc. And then let's directly come to the main point of this video, which is preparing your data for LSTM. So I here in this cell, I'm just defining this class config, which will have all my constants for the model. For example, seed is 42. I am doing a k-fold cross validation here. So my number of folds are 5, and selected folds is an array with the 5 folds denoted by 0, 1, 2, 3, 4. And defining my learning rate and what else? And then optimizer, batch size, total number of epochs that I want to train it for, which I'm setting at 300. Yeah, that's pretty much it. And then I have to go to the other files because within the notebook, then I'm directly running this k-fold, which is like the absolute final method, which will include within it the training and the feed and the LSTM class as well. So let's come first to my util file. And the first one for in the utils file is the evaluation metric calculation. And as per the competition's official evaluation metrics definition, this is what they say. The competition will be scored as the mean absolute error between the predicted and actual pressures during the inspiratory phase of each breath. Note this word, inspiratory phase, not the expiratory phase. And then they specifically say the expiratory phase is not scored. The score is given by modulus of x minus y, where x is a vector of predicted pressure and y is a vector of actual pressures across all breaths in the test set. So first I define my actual pressure vector, which by taking from the data frame, I take the pressure column and you take the values, apply toList, and finally np.array. And then this particular line weight equal to 1 minus np.array. So for this, you have to understand the u out column, as was mentioned in the official page of the Kaggle competition. There is an u out column in my data frame. So the u out is a binary variable representing whether the expiratory valve is open, that is 1, or closed, that is 0, to let the air out. U out equal to 1 is a expiratory phase. In simple terms, expiratory phase is breathing out, or in the case of an artificial lung, let the air out. The data for the expiratory phase is not helpful for the model. During the exhale, the ventilator pressure and the target pressure are nearly identified. Hence here I am dropping out u out equal to 1 data actually. And this was exactly what was done by many of the top scoring notebook in the competition, by many of the top rankers in the public leaderboard for this competition. That is, they completely dropped out the u out equal to 1 data. And the way I do that is with this line, that is, I am assigning weights of 0 when the u out value is 1. And that's the reason I am deducting these values of u out from the data frame from 1, because remember, u out can only take binary values as given in the original train.csv file, that is either 0 and 1. So when the u out is 1, this expression will become 0. And yeah, then with this assert method, I'm just checking the shape of all the relevant tensors as just equal. All right, then my k-fold method. So within this k-fold method is where I will apply the final train function on each fold and get my prediction. But first, to do that, I need to apply the group k-fold method here to get all my different folds, and that's why I'm using this group k-fold function here. It is coming from scikit-learn. And so if you note the splits equal to list and then group k-fold dot split, this entire expression right here, in this case the groups are defined by the breadth id column of the input data frame. So in group k-fold dot split method, which is what I'm using right here, this returns an iterator that yields tuples of train and validation indices for each fold based on the specified groups. By passing the iterator to the list function, a list of these tuples is created and stored in the splits variable. So each of these tuple in the splits variable has the a structure like train indices and validation indices, where train indices and validation indices are numpy arrays containing the indices of the training and validation samples for a specified fold. This list has k elements, where k is the number of splits specified when creating the group k-fold object. Alright, so that's where this line ends, and then I start these iteration looping over the splits variable. So here, what I'm doing is iterate over the generated splits using a for loop for each split. If the current fold index is in the config.selected folds, then perform the following steps, which is create a training data frame, that is df train, and a validation data frame, that is df validation, df val, using the train and validation indices from the current splits. And once you get your train and validation dataset for a particular fold, then you can apply the train method, which is what I'm doing here, to get your predicted validation and predicted test data with this train method. And that's the purpose of this line right here. And then finally, you just update two arrays, that is pred oof out of fold this array and pred test by appending and then by flattening the array. And that's what you return from the k-fold. That is, you are returning your out of fold prediction value and also the mean of pred test. And then I have this little util method seed everything. So here, mainly look at this line os.environment python hash seed, and I'm setting it to str, that is string format of this argument seed. So by default, Python uses a randomized hash function to prevent hash collision attacks. That is an attacker flooding a Python application with carefully crafted strings that cause hash collisions, leading to high CPU usage. So, however, this randomization can introduce non-deterministic behavior across different runs of the same script when using hash-based data structures like dictionaries and sets. So, to ensure consistent behavior across different runs, you can set these Python hash seed environment variable to a fixed integer value. That is what I'm doing here. When the variable is set, the Python interpreter will use the specified seed for its hash function, ensuring that the hash values for the same data are consistent across different runs of the script. And OS.environment, the one that I'm using here, is a dictionary-like objects in Python OS module representing the environment variables of the operating system. It allows you to read, modify, and create new environment variables that will be inherited by child processes spawned by your Python script. And one of these environment variable is Python hash seed. That's what I am modifying here by supplying my seed integer to this. And then in this torch manual seed, this line sets the seed for PyTorch's random number generator used in various operations like weight initialization in neural network. So by setting the seed, you ensure that the initialization and random behavior in PyTorch remains consistent across different runs. And I'm also setting the seed to torch.CUDA manual seed. This line sets the seed for PyTorch's CUDA random number generator, which is responsible for generating random numbers on the GPU. And finally, torch.backends.cudnn deterministic, I'm setting it to true. This line sets cudnn, that is NVIDIA's deep neural network library used by PyTorch, to use deterministic algorithm. Some CUDNN algorithms have non-deterministic behavior, which can lead to slight differences in the results for multiple runs. By enforcing deterministic algorithm by setting it to true, you ensure consistent behavior across runs when using CUDNN accelerated functions. And finally, this one, backends, I'm setting it to false. So this line disables the CUDNN benchmarking feature, which when enabled, CUDNN automatically selects the best algorithm for a specific operation based on the input size and hardware. However, the best algorithm may change between runs, leading to a non-deterministic behavior. Disabling the benchmarking feature ensures consistent behavior across runs at the expense of potentially suboptimal performance. But that's okay, because here I'm pretty much targeting everything to be deterministic. So so that's the whole purpose of this seed everything, and I'm going to use it within my train method that we are going to see in a second. And then I'm coming to the train file. This file has all the important functions over here. The first one is ventilator dataset. This is first I have the constructor, that is the init method, and then the len, and then data preprocess. So let's go through them one by one. So the init method here, look at this line particularly, self.df equal to df.groupby, then breath id, that is I am grouping by the breath id column. This means that all rows with the same breath id will be combined into a single group. And then I'm applying this .agg and passing list. So this function, that is .agg and list, this will aggregate the data in each group using the list function, which means that the values in each group will be combined into a list for each column. And then the len method, as usual, is returning the length of my data frame. And data preprocess, this is another important method here. So data preprocess, I am just preparing the tensors from the input data frame to be able to be passed into PyTorch model. So the first one is I'm getting all these R, C, and U in. So as if you remember, our original data frame was just this. So I have this R column, C column, U in, U out, pressure. So that's what I'm going to deal with right now. So let's go back to my train file. Yep. So this below block RACSUNs, very much what they do is they're responsible for preparing the input features for the PyTorch model. It reshapes and concatenates several NumPy arrays, calculates the cumulative sum of one of the arrays, and transposes the resulting concatenated array to match the expected input shape of the PyTorch model. So the basic structure is just this. I'm taking from my data frame, I'm just taking the R values and then applying toList on them to make it a NumPy array, and that becomes my RS. Exactly same thing I'm doing with CS and UINs, and then with these within this concatenation, I am doing I'm adding one extra dimension with this none keyword. And within the np.concatenate, that is this function right here, is used to concatenate the reshaped arrays along axis 1. The input to this is a list containing the reshaped arrays from the previous step. The result is a new NumPy array, that is after the concatenation, with the same number of rows as the input arrays and columns corresponding to the concatenated arrays. And finally, the result after the result of the concatenation, I'm applying transpose, that is 0 to 1. So this particular method calls the transpose function on the concatenated NumPy array and changes the order of the axis. Specifically, the input tuple of 0 to 1, that is, in this case, axis 0 remains in place while it swaps axis 1 and 2. This operation adjusts the shape of the input array to match the expected input shape of the PyTorch model, because the whole reason of this particular data preprocess is that I am preparing my input data to be fed into PyTorch model. And finally, this another standard method within this my validator dataset class, which is getItem. So it allows the dataset object to be indexed using square brackets, and it is used to fetch a single data point from the dataset given its index. The method is essential when creating custom PyTorch dataset to work seamlessly with PyTorch's data loader and other utilities. Alright, with that, this class is done, and next one is ventilator loss. And this ventilator loss is just the flow, and the concept is just the same as we discussed in our MAE calculation. That is, we ignored wherever u out is equal to 1, and that's how we adjusted the weights. The weight should be 0 when u out is equal to 1, because u out does not affect the model training. So similarly, ventilator loss is just exactly calculating the MAE, and here as well the weights is adjusted so that it will be 0 when u out is equal to 1, that is during the expiration phase. And after this, I have this little single line method for count parameters, and this is pretty much for logging. That is, whenever when training, during the training phase, I need to just log few parameters or few information, and that's exactly what this method is doing. It's just a single line return based on the if condition. That is, if all this argument is false, then I am returning all the model parameters. Otherwise, I am returning the model parameters where those parameters have their corresponding requires grad. Save model weights, that's also a quick small method just for saving the torch model. Alright, now this fit function, that's slightly bigger one, so let's go through that. Oh, I forgot to discuss another quick method here, worker init function. So this function sets the seed for NumPy's random number generator using the calculated unique seed value for each worker. So the most important thing is that I am applying np.random.seed, but inside seed, instead of passing a single integer value, I am calculating that value so that it will dynamically change. So this np.random.getState, and then I'm taking 1 from the first list and then the 0th element. So this expression adds up, actually this function returns the internal state of NumPy's random number generator. The state is a tuple with multiple elements where the second element, that is indexed by 1, is an array corresponding to the current seed value, and from that I'm taking the 0th element. To that I'm adding the worker ID. So overall this expression will make sure that each worker gets a unique seed for the random number generator, thus generating unique random sequences. Generally with np.random.seed, we are controlling the seed value that initializes the internal state of the random number generator. From that state, the generator then produces a sequence of random numbers. Seed values provide control over randomness, since changing the seed gives you a different sequence, and using the same seed value on the same random number generator will result in the exact same sequence of random numbers. All right, now going to my fit method. So this fit method will be used during my during the training phase, and it takes a lot of parameters, all pretty much standard ones. You can obviously, just looking at the parameters, it's obvious. It takes a model, train dataset, val dataset, optimizer, epochs, batch size, val bs, warm up prop, learning rate, verbose, etc. So first I'm defining the optimizer, and I'm defining that with get attr. To that I'm passing torch.optim. So this get attr, this function called retrieves a reference to the optimizer class specified by the optimizer string variable. For example, if optimizer is Adam, then get attr torch.optim and then passing optimizer returns a reference to torch.optim.adam class. And model.parameters, this is a method call on the model object, which is an instance of a PyTorch neural network. The parameters method returns an iterator over the model's trainable parameter, that is weights and biases. These parameters will be updated by the optimizer during the training process. So this get attr is a built-in Python function, not specific to PyTorch. It is used to retrieve the value of an attribute from an object by providing the object and the attribute's name as a string. It allows for dynamic attribute access, such as when you don't really know the name of the attribute that you want to access beforehand, or when you want to iterate over a list of attribute names. So in PyTorch, get attr can be used to access attributes of various objects like models, layers, or tensors. And then I define the train loader and data loader by using the data loader module of PyTorch. And this data loader module takes quite a bit of arguments within them. And first, train dataset, batch size, shuffle, I'm making it to true, drop last. Number of workers, pin memory, I'm setting it to true. And note the last one, which is worker init function. This is a custom function that we defined a while earlier and we discussed. So this worker init function is an optional function that can be used to set up the worker's environment or seed when using multiple worker subprocess to load data in parallel. So it ensures that each worker operates with a different seed, helping maintain reproducibility in the training process. So similarly, I also have my validation loader by using the same kind of data loader module, and my loss function is an instance of ventilator loss that we defined earlier. And before starting the epoch training, I define few more configuration objects here, number of warm-up steps, training steps, and scheduler. And then here I start the looping through the epochs. Pretty standard code here. First I do model.train, model.0grad, start time. This is just for logging. So I loop through for each data input through my train loader, because that will give me batch by batch data. So I'm moving through those input data here in this loop. And the flow is pretty simple. You execute your model first, which will give you the prediction. And obviously you pass the model input to your GPU device. And then you get your loss by applying the loss function. And to the loss function, you pass your prediction, your actual data. And then you take the mean of that. And after loss, you just calculate loss.backward to update my weights. And average loss will just be all the individual losses divided by length of the train loader. And after that, optimizer.step and scheduler.step. And then put the model in evaluation mode and define a new preds array to be an empty array, which we will continue to update in the next loop. So in the next loop, the only difference is that now I'm looping through the val loader. Previously, we were looping through my train loader, and that's why there I use the gradients of PyTorch. But now, because it's an evaluation, I don't need the gradients layer. So I am defining a context manager with torch.noGrad. And now again, executing the model, which will give me the pred, calculating the loss, calculating the average validation loss, and then updating this preds array with the average validation loss. Sorry, this preds, to the preds, I'm just appending the individual pred after applying detach.cpu numpy, so that it will append just the pure numpy value. And after the loop, you calculate the MAE, mean absolute error, by applying our previously defined MAE calculation, which is coming from a utils function. And that is I'm calculating for validation dataset. And then this block of code is just for logging at various stages of my training. I need to log various information. That's the whole purpose here. And then this LSTM model class, which defines my main model, because remember this exercise is a bidirectional LSTM model implementation. So here I have different methods. First the init, and then my various layer definition. So I'm having a linear ReLU, another linear ReLU. Also, this is the most important LSTM layer right here. And in the bidirectional, I'm setting it to true. And from applying the nn.sequential, I will get a logits. And within the sequential, again, I'm passing linear, ReLU, linear. And this logits is what I'm going to use within my forward method right here in this line. And finally, from the entire class, I am returning this prediction. And then the very last and important method, train method. This is where all the juice will flow. And like we discussed before, to make these entire exercise and the model reproducible, we had defined a seed everything method in utils file. And I'm running it as the very first line within my train method. And so that everything becomes kind of deterministic. And then this is my model. So this is the LSTM model class. To that, I pass all the required argument. And then model.0grad, because in the next step I'm going to start the training. So I apply 0grad right here. Define my dataset using ventilator dataset class. So I have train, validation, and test dataset. And then apply the fit method that we defined earlier. From the fit method, I get pred validation. And I also have a little predict method, which I actually have defined after the train method right here. So predict method will take model, dataset, batch size, and device, and it will actually start from the very beginning with the evaluation mode with model.eval, and then I get the loader, that is a data loader, using the data loader module. And finally, from this predict method, I get a NumPy concatenated array called preds by evaluating the model. And that's a predict method I'm using right here within my train method. And finally, I am just saving the model here. And from the entire train method, I return these two NumPy arrays, pred validation and pred test. Now, this train method is what I use within my kfold that we have discussed earlier. That is, kfold will first do fold the entire dataset using group kfold, and then while enumerating over the splits variable, which is list variable after applying the group kfold, so then I enumerate over the splits variable, and for each loop I apply this train method right here. And when I apply the train method, that I get predval and predtest, these two NumPy arrays, and these two NumPy arrays I continue to append to these variable predOOF and predtest, and that's what I return from this kfold. Now coming back to my notebook, this kfold is what I apply right here. So this is my df train and df test we have already defined earlier, and immediately after defining all the config related classes or constants, I apply kfold right here. And after applying the kfold as a return from this function, you get your pred out of fold and pred test. And this pred test is your all important predicted target data that you need to submit to Kaggle competition, and the rest of the code is just simple. I'm just creating a CSV file from the pred test, and that's what I'm submitting. So at the start of the competition, within the first 2-3 weeks, this particular notebook created a score of 0.37, which was like the top 6 to 7% in the competition, but later it fell behind because anyway, the whole purpose of this was to implement a baseline bidirectional LSTM. I did not do any crazy feature engineering, because in this competition there were quite a bit of opportunities to do or create more engineered features, but that was not part of this exercise because it was a baseline implementation. Alright, that pretty much wraps up this video, and do stay tuned because over the coming weeks I will do quite a few more on similar lines. So see you in the next one.